Over the 2018 OCR AS level paper 1, and we are doing section B. This question is about elements from the P block of the periodic table. Silicon exists as a mixture of 3 isotopes, so silicon 28, silicon 29, and silicon 30. Complete the table to show the atomic structure of silicon 30. Right, so first of all, in all isotopes, the number of protons stay the same because it's still the same element. So if we go to the periodic table and we look for silicon, we can see it's a proton number of 14, and number of protons is equivalent to number of electrons, so that's also 14 because this is not an ion. And number of neutrons will be the mass number minus the number of protons, so 30 minus 14 gives us 16. A sample of silicon is analysed by mass spectrometry. The mass spectrum shows peaks with the relative abundances below. Calculate the relative atomic mass of silicon in the sample. Give your answer to 2 decimal places. So whenever it's mass spectrum, we just multiply these numbers together and we add it to each other. So 28 times 9, 92.23, plus 29 times 4.68, plus 30 multiplied by 3.09, we always divide by 100 and we get 28.109, 2 decimal places makes it 28.11, and that's our final answer. To check if we're correct, we have to go to the periodic table and we check if the mass number has a similar answer to what we have over here. If it's close in the answers, that means we are correct. Phosgene COCl2 exists as simple molecules. The displayed formula of a phosgene molecule is shown below. Draw a dot and cross diagram of a phosgene molecule, show the outer electrons only. Okay, so we can see it has this shape, so that's what we're going to do. Carbon in the middle and chlorine to the sides and oxygen to the right hand side. We can see that there's a single bond between chlorine and the carbon and double bond for the oxygen. So we're going to do the double bond for the oxygen over here and the single bond with the chlorines. And we know that carbon has 4 electrons in the outer shell, and that's represented here by the dots. And it has gained 4 electrons, 2 from the oxygen and 1 each from the chlorine, giving it 8 electrons in total. That's a full outer shell. We move on to the oxygen. It has 6 electrons and it's gained 2 from carbon, so that's 8 in total. And chlorine has 7 electrons and it's gained 1 from the carbon, as we can see here and here, making it 8 electrons and full outer shell. So we know that our drawing is correct. Name the shape of a phosgene molecule and explain why it has a shape. Okay. So first of all, this shape is a trigonal planar, and this is because the shape doesn't depend on if it's a single bond, double bond, or carbon bond, but they're all treated as the same. So this is seen as 3 bonds, and so it's trigonal planar because it's 3 bonding regions, and it's shaped in this way because the bonds have to repel, so electron pairs move as far apart as possible from each other. That's its repulsion, and that's why we have the shape, as opposed to, with chlorine being over here, but chlorine's actually, so instead of having the shape looking like this, it's not. It's because these bonds repel, and so they're as far apart from each other as possible. Why are silicon, carbon, oxygen, and chlorine all classified as p block elements? So straight away, it's because they have the highest energy electron in the p orbital. So p block because the last electron is in the p orbital. This question is about compounds of magnesium and phosphorus. A student plans to prepare magnesium phosphate using the Redox reaction of magnesium with phosphoric acid. In terms of the number of electrons transferred, explain whether magnesium is being oxidized or reduced. So we go over here, oxygen is an element on its own, so it's going to be 0. And next time we see, magnesium is an element on its own, so it's going to be 0. And next time we see magnesium, the product is over here, and this is the molecule has made, and we know magnesium is in group 2, and therefore it will have a charge of +2. If you didn't know that, we know that phosphate is PO4 -3, and we know we have 2 lots of it, so that's -6 in total, and it has a total charge of 0, and so we need to have magnesium counteract that charge. Therefore, magnesium needs to have a total charge of +6. There's 3 lots of magnesium, so 6 divided by 3 is 2. But the easy one to note is that magnesium is in group 2, and therefore it will have a charge of +2. And we have gone from 0 to +2, therefore it's been oxidized, because oil rig, oxidation is loss of electrons, reduction is gain. And we say because magnesium has lost 2 electrons. A student plans to add magnesium to 50 centimeters cubed of 1.24 moles per decimeters cubed of phosphoric acid. Calculate the mass of magnesium the student should add to react exactly with the phosphoric acid. Give your answer to 3 decimal places. Right, so whenever there's quite a few numbers, I always do this. First thing I do is I write the equation and I fill it in with these. So I do the ratio, the concentration, volume, moles, and only if they've asked for the mass, that means I need to include the mass and the MR somewhere in my calculation. So I do this type of box, and they've given me the equation over here. You usually only see the first half of the equation. So I've written magnesium plus phosphoric acid, and this is the ratio, so I have a 3:2 ratio. And now I start filling in my box. So the constant, so if I go over here, the first thing I see is 50 centimeters cubed. So it tells you that I have magnesium is going to be added to 50 centimeters cubed of phosphoric acid. And so I go to the volume and I've added 50 under phosphoric acid, and I converted decimeters cubed, so 0.05. And I've used that number. Now, 1.24 moles per centimeters cubed of phosphoric acid. So I go to the concentration and I add 1.24. So I use that up. And calculate the mass, so that's what they want. So I go to the mass and I put a question mark. Therefore, I visualize what I have and what I want. So straight up, I can see that if I've got concentration and volume, I can calculate the moles, and moles is the only thing I can transfer to other sides. And so if I work out the moles of phosphoric acid, I can take that to the magnesium side, and if I have the moles and I can calculate the mass of magnesium, just straight away from the periodic table, then I can calculate the mass. So that's how I'm going to work. And so I've got the concentration, I've got the volume, and so to work out moles, I times these together, and so I do that and I get 0.062. So that's my first step of working out. I've got 0.062 moles. However, this is for 2 moles of phosphoric acid and I need 3 moles of magnesium. So it's quite hard to transfer to the other side because it's not like a 1:2 ratio where I can just times by 2 or divide by 2. So what I do is that if I divide this number by 2, I will have a molar ratio for 1 of phosphoric acid, and therefore if I've got 1, I can times it by 3 to get magnesium, because going from 2 to 3 is harder. So if I divide it by 2, then I get 1, and if I get 1, I can just times this by 3 and to get the answer for magnesium. So that's what I'm doing over here. I do 0.062 divided by 2, because that's the number I have over here, and then I multiply it by 3, and that gives me 0.093 moles, and that's the moles for magnesium. So now I have moles. I can calculate the MR to get the mass. The MR is just for magnesium, so I go to periodic table, 24.3, and therefore if I multiply these together, I should get the mass. So I do 0.093 multiplied by 24.3, and I get 2.26 grams, and that's my final answer. How could the student obtain a sample of magnesium phosphate after reacting magnesium with phosphoric acid? So there's like 2 ways you can do this. So once we've reacted it and we get a solid, we can separate the solid, and we can do that by filtering to get the precipitate out. Another way you can do it is by removal of water. So what we mean is we just dry or evaporate the liquid, and we should get the solid remaining. And this is because we're trying to get this out. Magnesium phosphate can also be prepared by reacting phosphoric acid with a compound of magnesium. Choose a suitable magnesium compound for this preparation and write the equation for this reaction. So there's multiple ways you can do this, because there's many magnesium compounds you have come across that we can use. So you've come across magnesium oxide, you've come across magnesium hydroxide, and you've come across magnesium carbonate. These are all magnesium compounds, and we can use them in the reaction to react with phosphoric acid to get a compound of to get magnesium phosphate. So I've written 3 of them over here. So magnesium oxide, if I react with phosphoric acid, then I get the product that they're wanting, which I've stated over here as well. Just copied that. And because it's an oxide with an acid, you always produce H2O. Then I go to balance it. So I got 3 magnesiums here, and I got 1, so I write 3 automatically over here. I have got 2 lots of phosphate, so I write 2 over here. And now I've got a total of 6 hydrogens, and so I write 3 over here to make 6. And actually that just balances out my oxygen, so I've got all the same oxygen as well. Next compound is my magnesium hydroxide. I combine that with the phosphoric acid. I should get the same product that they want. And a base and an acid will give me water as well. And so I balance that as well because 3 lots of magnesium, so I add 3 over here. 2 lots of phosphate, so I write 2 over here. And that gives me a total of, so I got 6, and I've got, so in total 12 hydrogens on this side, so I write 6 hydrogens over here to make 12, and when I count all my oxygens, they've all been balanced out. Finally, the last compound I can use is magnesium carbonate, and I combine that with the phosphoric acid, and I get the compound that they're asking for. But whenever we use an acid and a carbonate, we get water and carbon dioxide. Now let's balance it off. So I have 3 magnesium, so I put 3 over here. I've got 2 lots of phosphate, so I add 2 over here, and I've got 3 lots of carbon, so I put 3 over here, and I've got a total of 6 hydrogens, so I add 3 over here, and that automatically balances out all my oxygens. And so that's 3 different ways you could have done this. Phosgene pH3 is a gas formed by heating phosphorus acid H3PO3 in the absence of air. So this is what it is. 3.2 times 10 to the power of minus 2 moles of phosphorus acid is completely decomposed by this reaction. Calculate the volume of phosphine gas formed in centimeters cubed at 100 kilopascals pressure and 200 degrees. Okay, so automatically when they bring in volume and pressure and temperature and there's moles, then this equation should pop into mind. And since we want the volume, we rearrange the PV equals nR to be rearranged by taking volume to the other side, pressure to the other side, and we get this equation. Now we fill it in using what we have and what we want. So we want the volume, and let's fill in what we have. So the pressure, we have kilopascals, and in this equation we need pascals. So to convert from kilopascals to pascals, we times by 1,000. So 100 times by 1,000, we get 100 times 10 to the power of 3 pascals. So that's our pressure right here. Next thing is R, and R is a constant, so always it's the same with every single question with PV equals nRT. So it's 8.314, so we have that. If we go to temperature, we have 200 degrees Celsius and temperature being kelvins, and to convert from degrees Celsius to kelvins, we add 273. So 200 plus 273 gives us 473, and that's our temperature sorted. Now for moles, we've been given 3.2 times 10 to the power of minus 2 moles for phosphorus acid, and we want the phosphine gas formed. So what we see is this is the number of moles being given. So we have 3.2 times 10 to the power of minus 2 moles for phosphorus acid, but this is for a ratio of 4. Yeah? So this number is for a ratio of 4, and we want for pH 3. Now we can move moles to the other side. So if we have 4 moles, which is 3.2 times 10 to the minus 2, we have to divide by 4 to get the number of moles for 1 mole of pH 3, because we have no number in front over here, so it's 1. And so that's what we're doing. We're dividing by 4, and we get 8.10 times 10 to the power of minus 3 moles. So now that we have everything here, we plug it into the equation, and we should get 3.146 times 10 to the power of minus 4 meters cubed. Now, in the question, it says calculate the volume of gas in centimeters cubed. And so to convert from meters cubed to centimeters cubed, you divide by a million. And that's because you go from meters cubed to decimeters cubed, divide by 1,000. Oh, sorry, you multiply by 1,000. So from meters cubed to centimeters cubed, you multiply by a million. And so we do this because from meters cubed to decimeters cubed, we multiply by 1,000. And from decimeters cubed to centimeters cubed, we multiply by 1,000 again. So if we just straight away jump it, then it's multiplied by a million. And so we times 10 to the power of 6, which is a million, and we get 315 centimeters cubed. And that's our answer. When exposed to air, phosphine spontaneously ignites, forming P4H10 and water. Construct an equation for this reaction. Okay, so phosphine, which they've given us over here, is pH3. So we write pH3, and it says it's going to expose to air, so we know air is O2. And it tells us it forms P4H10 and water. So we have our equation. Now let's balance it out. We've got P4010, not H10, sorry, P4010. O10. So we got 4 lots of phosphate, and so we put a 4 in front of the pH3, and we can see we've got 10 lots of sorry, we don't have 10 lots of oil. No, it's easier to start with hydrogen because it's easier to start with to use something that only occurs once. So for example, oxygen occurs here and here, therefore it's best to leave it last. So now let's go to the hydrogens. We've got a total of 12 hydrogens, and so we put 6 in front of the H2O to make 12 hydrogens. And if we count that in total, we have made 16 oxygens, and so we put an 8 in front of O2 and we balance it to make 16. This question is about energy changes and rate of reaction. Magnesium reacts with aqueous silver nitrate AgNO3, as in the equation over here. A student carries out an experiment to determine the enthalpy change of this reaction. The student adds 25 centimeters cubed of 0.512 moles per decimeter cubed of silver nitrate to a polystyrene cup. The student measures the temperature of the solution. The student adds a small spatula measure of magnesium powder, stirs the mixture, and records the maximum temperature. And this is a temperature reading initial and maximum. Calculate the enthalpy of reaction in kilojoules per mole for the reaction here. Give your answer to an appropriate number of significant figures. Assume that the density and specific heat capacity of the solution are the same as for water, and that all aqueous silver nitrate has reacted right. So they want kilojoules per mole, and to get kilojoules per mole, so whenever you see that little minus 1 over here, that means we had to have divided those units together. So we have to do kilojoules divided by moles to get kilojoule per mole. And we get the kilojoules because whenever we use this type of experiment, we always use Q equals mc delta T. And the moles we know we get from concentration equals moles divided by volume, so this equation. So this experiment, we use Q equals mc delta T, and Q gives us joules, which we can get kilojoules from. So let's see, Q equals mc delta T. We have everything here to work it out. We've got 25 for the mass, and we've got 0.512 for the concentration, which is C, and, oh no, sorry, capacity, no. We've got 25 for the mass. The C is the heat capacity, which is a constant, which is for water, because they've said use the water, which we know is always 4.18. That's what we have over here, times by delta T, which is a change in temperature, which we have over here. So 47.5 minus 19.5 gives us 28. So then we multiply these together, and we get 2,926 joules, and we want kilojoules, so we divide by 1,000. And so we've got a kilojoules number. Now, moles, we can work out moles because we do C times V, and so C is 0.512, so we've used that up here, times by the volume, which we have 25, but we get it to decimeters cubed, so we convert it, divide by 1,000, and so if we multiply these two numbers together, we get 0.0128 moles. So now we've got the kilojoules and the moles, and in order to get them into this form, then we need to divide them. So 2.926 divided by 0.0128 gives us 228.59. So that's our answer. However, this is for this reaction, and we're using it for silver nitrate, because it says over here, assume that all silver nitrate has reacted. We've got 2 moles of silver nitrate over here, whereas this is being used for 1 mole of silver nitrate, so therefore we times by 2, and that gives us 457.1875, and we need to give an appropriate number of significant figures, so we have 457. Some of you might get 458 because of rounding over here, but both are correct, but I would always suggest leave rounding to the last answer, so don't round early on. And this is our answer. At the end of the experiment, the student adds a few drops of aqueous sodium chloride to the reaction mixture in the polystyrene cup to test whether all the aqueous silver nitrate has reacted. Explain how the results, which show whether all the aqueous silver nitrate has reacted, including an equation for the state symbols in your answer. Okay, so we come across silver nitrate when we're testing for halides, and therefore, if we have silver nitrate remaining, if we add, like they've said, sodium chloride, because the chlorine, so the chloride ions will combine with the silver ions, we get a white precipitate forming, which is AgCl. So this tells us that if a white precipitate forms, then we know that not all the silver nitrate has reacted, because there was still some silver nitrate left over that reacted with the chloride ions to form the white precipitate. However, if we put sodium chloride and we have no white precipitate forming, that means all the silver nitrate did react, and therefore we can't have this reaction. Using the Boltzmann distribution model, explain how the rate of reaction is affected by temperature. Okay, so you are provided with the axis below, which should be labelled. Okay, so the Boltzmann distribution, it's always number of molecules on the y-axis, and on the x-axis is the energy. And so this is what it usually looks like. So we've got, goes up like this, and it goes down. So we label that as T1 because we're using temperature. And so T2 would show what happens when we increase temperature. And so what happens, the graph skews to the right-hand side. So it goes to the right and it remains higher. So it does come down, but it's still higher than T1. And that just shows you that more molecules will have the energy greater than the activation energy. And so that's basically the area under the curve. So this is what you have. This question is about saturated hydrocarbons. Compound A, B, and C are saturated hydrocarbons. The structures and boiling points of A, B, and C are shown below. So this is what we have. Use the structure to explain what is meant by the term structural isomer, and explain the trend in boiling points shown by A, B, and C in the table. So the structural isomer just means that they have the same molecular formula. So all of them will be, 1, 2, 3, 4, 5. So it will be all C5, H, whatever if we count it. But they'll have a different structural formula. And so same molecular formula, but the way how they're drawn is different. So that's what's just meant by structural isomer. So now they want the trend in boiling point. So as you can see, boiling point decreases. So A is greater than B, which is greater than C. And boiling point decreases because there's more branching that occurs. And more branching means less surface contact, so fewer London forces, because this is what actually happens. So if we have this, then this is touching with another molecule of itself. So we can see there's a lot of contact points. But if we use this one, then here's what's happening. There's less contact points with each other, whereas here there's more contact points. And so you will have more London forces here. So as we have more branching, we'll have fewer London forces. And therefore, we will need less energy to break these London forces, so the intermolecular bonds, because there's less of them. And that's why boiling point decreases. Compounds A, B, and C all react with chlorine in the presence of ultraviolet radiation to form organic compounds with the formula C5H11Cl. Name the mechanism for this reaction. So whenever there's ultraviolet light and there's chlorine, so a halide, we have radical substitution. Complete the table to show the number of structural isomers of C5H11Cl that could be formed from the reaction of chlorine with A and B. Okay, so this is A and this is B. And if we take A, they want the number of isomers. So the same molecular formula but different structural formula. So that means we need to get a chlorine and we need to, sorry, I can't say this. And we need to position the chlorine so that they will have the same molecular formula but they're laid out different. So the first one, most obvious, is sticking the chlorine to the end. I can put it here or I can put it here because this is the same thing. We flip it, so I'm going to choose to put it over here, so that's one. Another one is I can put it on the second carbon, so I can put it over here, or I can put it over here. Doesn't matter, the same thing, so I'm going to choose to put it over here, so that's my second isomer. Third one is I can put the chlorine in the middle. So I can draw it up or I can draw it down, it doesn't really matter, it's the same thing. And therefore I can only have a total of 3 different isomers, so that's for A. For B, which is this structure, I can position the chlorine over here, or I can position it over here. It's still the same thing. So I'm going to choose to put it over here, so that's 1. I can then move the chlorine to the second carbon over here, so that's another 1. I can move the chlorine to the third carbon over here, so that's 3. Or I can put it right at the end, but this counts as another isomer because putting chlorine over here or over here will not result in the same isomer because you have this. If this didn't exist, then this and this would be the same thing. But because we've got this chlorine over here, then we put this carbon over here. When we put chlorine on the end, it will be a different isomer to what we have here. So if I draw it over here, this and this is not the same thing, because if you flip it, it still won't result in the same thing. Complete the table to show the number of structural isomers. Oh, sorry, yeah, we've done that, so 3 and 4. The reaction of compound A with excess chlorine forms a compound D, which has a molar mass of 175.5. So that's just a symbol for MR. Draw a possible structure for compound D and write the equation for its formation from compound A. Use the molecular formula in the equation. Okay, so first of all, if we go to compound A and we calculate the MR, we will have C5H12, and that gives us 72. This one needs to have an MR of 75.5. Now, chlorine is normally 35.5, and because we have a 0.5 here, that indicates that we will have an odd number of chlorines. Because if it was an even number of chlorines, then we wouldn't have a decimal. So I've written over here what happens if we add 1 chlorine. So it will take our MR up to 107.5, and then we have to minus 1, because in order for chlorine to join, we have to remove 1 hydrogen. And so that still doesn't give us 175.5. If we add Cl2, it gives us an even number, so that's definitely not our answer. And, sorry, I meant a number with no decimal place. And if we add 3 chlorines, then we get 178.5, but we need to minus 3 hydrogens, because we have removed 3 hydrogens in total to add the chlorines, and that gives us 175.5, which is what they're looking for. You can add chlorines in any way you like. I've just decided to draw them like this. It doesn't matter where you actually position them. And they want the equation, so C5H12, we've added Cl2, and that gives us C5H9Cl3 plus HCl, because we've removed the hydrogens when we've attached the chlorine, and chlorine comes like this. One of these chlorines will attach to the C5H12, removing the hydrogen, and the other chlorine will attach with the hydrogen that's been removed. So it's not both these chlorines that will be attaching, it's one of these chlorines that will attach here, and the other chlorine will favour to join with the hydrogen that has been removed. So that's why we get HCl. Now, the number of chlorines is not balanced. We've got 3 over here, whereas we've got 2 over here, so we write 3, and we get a total of 6. And it balances over here, because if we have 3 chlorines, we've got 3 chlorines over here, and okay, right, it's confusing if we start with chlorines, because they occur on more than one product. So if we start, we've got carbon and carbon's both balanced. Hydrogens, we've got 12 hydrogens here, we've got 9 over here, and we need to make them equal. So if we add 3 over here, that gives us a total of 12 hydrogens. And so, but now we have a total number of 6 chlorines, and we've got a total number of 2 chlorines over here, so we add 3 over here, and that balances out to 6. Yeah, so my tip is always to balance out using the atoms that don't occur on both products. So start with only one product, because it gets harder if you try to use a product that has both of the atoms. So for example, chlorine here and chlorine over here, so it's harder. This question is about reactions involving alcohols. 3 reactions of an alcohol E shown below. So complete the figure to show structures of organic products formed in the reactions. Okay. So this is what we have, and when we heat it with sulfuric acid, we get a dehydration reaction. So that means is that we will be forming a double bond and removing water. So the double bond will form right in the middle, and remove a molecule of H2O, it doesn't matter. So we've removed an OH from here, and remove a H from here. So the OH must be from one carbon, and the other hydrogen must be from the other carbon. It can't be from the same carbon, because then this carbon will still have 5 bonds. So for example, if we remove this one, then this carbon will still have 3 bonds, and we do this one, so 4 and 5. So that doesn't work out. So you have to remove hydrogen from the opposite carbon, from the adjacent carbon. So that's H2O removed, and we form a double bond. And that's what happens when we add sulfuric acid and we heat. Now, we have potassium dichromate and sulfuric acid, but we have distillation and reflux. This is a alcohol. It's a primary alcohol, because the the OH group is connected to a carbon, which is connected to one carbon only, so that makes it a primary alcohol. And if we distill a primary alcohol, we have the conversion to an aldehyde, and it will stop because we distill it out. Whereas if you continue to reflux, you will get a completion, so you get carboxylic acid being made. And so an aldehyde is when you have a double bond between the oxygen and we have a single bond with the hydrogen, so we have this over here. So we only remove H2. And carboxylic acid, we will also have a double bond, and we will have an OH. So that's called a carboxylic acid. So what happens when we reflux, and we also just remove H2. So I think what we need to remember is that primary alcohols reflux to aldehydes, and if we continue to, they will be distilled into an aldehyde, but if we continue the reaction to reflux, we will get carboxylic acid. What's the systematic name of alcohol E? So alcohol E is this, and we take the number of longest carbons. That's 1, 2, 3. 1, 2, 3 because we name it from where the alcohol is, and if that's 3 carbons, and we know it's propane, and we need to mention where the OH is. So this is the first carbon, because the group needs to be attached to the lowest number of carbons. To the smallest number of carbons. That's C1, C2, and C3. So that's propan-1-ol we have over here, but we need to mention that we have a side group over here. So that's CH2, so that's a methyl, and we need to name this position, so it's 2-methylpropan-1-ol. Remember that this is just a CH3 that goes like this, so this is not an extra group because it's part of the carbon chain. So we have 2-methylpropan-2-ol, propan-1-ol. An alcohol can be prepared by hydrolyzing haloalkane with aqueous sodium hydroxide. Outline the mechanism for this reaction, so curly arrows and irrelevant dipoles. Okay, so I'm just going to draw this. So C2H5, and we have CH, which I've drawn over here, and Br and CH3. So this is what we have over here. And the first thing is, when we get the sodium hydroxide, it will be the hydroxide that will cause the attack. And so it goes to the carbon, and there's a dipole, so delta plus and delta negative, and that will cause the bond of bromine to break away, and the hydroxide will take its place. So this is what we get. So we just get the switching. And this is a nucleophile, so it's nucleophilic substitution. This is the reaction. And we get bromide ion as the product because it has been removed. The infrared spectrum for C2H5CHBr CH3 is shown here. The CBr bond absorption is labelled, so over here. Outline how infrared spectroscopy can be used to show that the bromoalkane functional group has reacted and the alcohol functional group has formed. Okay, so we know that, so basically asking how do we know that this has happened? Yeah, so how do we know that this reaction has occurred? Well, first of all, we know that the CBr bond is broken, therefore this peak will be removed because it's no longer in the product. And we will have a formation of an COH peak that will appear. And usually these appear around over here. So we get this forming over here. So we have the CBr peak disappearing and the COH alcohol peak appearing. And that's it.